In this video, I'm going to show you how to correctly calculate porosity in 3D Slicer by properly extracting the pore volume from your sample. I will also cover a few important pre-processing steps that you need when working with non-DICOM image stacks, so you can bring your data into 3D Slicer without running into problems later on. The sample I will use in this tutorial is a micro-CT scan of a sandstone with a diameter of 6 mm and a height of 10 mm, scanned at a resolution of 18.5 microns. This workflow applies to other similar samples as well. Now, if we look at an XY cross-section of the sample, you will notice that the pores appear black, while the grains and solid material show up as bright gray values. But here is a really important point that is often missed. The surrounding air also appears black, exactly the same as the pores. What I often see is that people simply threshold the grains, then directly calculate porosity. This usually leads to unrealistically high porosity values, because everything that appears as black, including the surrounding air, is counted as pore space. In this tutorial, I will show you how to properly separate the pore space from the surrounding air, define the bulk volume, and calculate porosity values that actually make physical sense. Alright, let's start by loading the dataset. Since my dataset is a PNG stack, I need to use the Add Data button. For simplicity, I will select Choose Directory to Add, then navigate to my dataset folder. Once I'm there, I click Select Folder. The nice thing about using Choose Directory to Add is that 3D Slicer automatically categorizes the files inside the folder. For example, you can see that the single text file in my folder is detected separately. Since I don't want to load that file, I will simply uncheck it. Here is my image stack. Before loading the data, it's very important to check the show options and make sure that single file is not checked. If it is checked, only one image from the folder will be loaded instead of the full stack. Once that's confirmed, I click OK, and now our dataset is loaded. Using the mouse wheel, I can scroll through the slices of my sample. And with this Reset button, I can always return to the default view. The very first thing I usually do after loading a dataset is check whether it was loaded as a vector volume or a scalar volume. Image stacks like this are often loaded as vector volumes, meaning they contain 3 channels instead of a single grayscale channel. To check this, I hover my mouse over one of the 2D slice views and look at the data probe window. If I see 3 similar numbers next to each other, that means the dataset is loaded as a vector volume. As you can see here, we do indeed have 3 values. For many functions in 3D Slicer, we need a scalar volume, so we need to convert this. To do that, I go to the module finder and search for vector to scalar volume, then switch to that module. Here, I make sure that the input vector volume is my dataset, which in this case is the sandstone. For the output scalar volume, I create a new volume and give it a name. I'll call it sandstone underline scalar and press OK. Then I click Apply. Now, if I hover my mouse over the 2D slice view again, you can see that there is only one number, which represents the grayscale intensity. Next, we need to make sure that the resolution of the scan is entered correctly. Image stacks usually do not contain spacing information, so we have to enter this manually. From the module drop-down menu, I choose Volumes. Here we can see 2 volumes, the original dataset and the new scalar volume I just created. I click on the scalar volume so it becomes highlighted. In the volume information section, in front of the image spacing, we can see that the spacing, which is the resolution, is set to 1 millimeter. And we know this is not correct. We know that the resolution of this scan is 18.5 microns. So I enter 0.0185 millimeters. Since this is a micro CT scan and it is isotropic, the spacing is the same in X, Y, and Z direction. So I copy this value and paste it into the Y and Z fields as well. You might notice that the sample disappears from the 2D slice views. That's completely normal. We just need to click the center button at the top of each slice view, and the sample will appear again. Now our dataset is ready. Next, we move on to segmentation. From the module drop-down menu, I go to Segment Editor and add my first segment. I double-click on it to rename it, and let's call it bulk volume. I leave the color as it is. The bulk volume represents the grains plus the pores inside the rock sample. To create it, I will first segment the grains and then expand that segmentation into the pores. I start by selecting the threshold function. As you can see, the grains are already nicely selected. I can adjust the gray value range using this slider, and somewhere around 70 looks quite good. Then I need to click Apply. Now, we have our first segmentation. At this point, only the grains are selected and the pores are still excluded. To include the pores, I use the smoothing function. In the smoothing method, I choose closing, which expands the segmentation into the pore spaces. Here we need to be careful with the kernel size. By default, it's set to 3 millimeters, which is far too large for this dataset. At our resolution, that would correspond to a cube of about 163 by 163 by 163 pixels. Instead, I will use a kernel size of 0.2 millimeters, which corresponds to approximately 11 by 11 by 11 pixels, and then click Apply. From experience, if the kernel size gets larger than about 20 to 25 pixels, the process can take a very long time. That's why I usually try to stay below 15 or 10 pixels. After a few seconds, the operation is done. You can see that many of the pores are now included in the segmentation, but some of the larger pores are still missing. What I could do at this point is simply increase the kernel size to a very large value and try to close all pores in one step. However, there are two problems with that approach. First, the process would take a very long time, especially for larger datasets. And second, using a very large kernel size can introduce artifacts in the segmentation. That's why I prefer to keep the kernel size relatively small and handle the remaining pores in a different way. To handle those remaining pores, I use a very useful segmentation extension called Surface Wrap Solidify, which you can download from the extension manager. This extension wraps around the existing segmentation and allows us to close all holes and unselected regions inside it. I leave the region set to outer surface, set the output to override segment, and click Apply. You could also use this extension directly after thresholding the grains, but since there are many pores, the process would take much longer. Combining the closing smoothing method with Surface Wrap Solidify works both faster and more reliably. After a few seconds, the process finishes, and you can see that all pores are now nicely included in the bulk volume. Let's also take a look at it in 3D. If there are any sharp edges, like here, we can smooth them out using smoothing. Changing the method to opening, keeping the kernel size at 11 pixels is okay, and click Apply. Now we have a clean and smooth bulk volume that includes both grains and pores. Next, we create another segment. I add a new segment, name it Pores, and change the color to red. Using threshold again, I select the pores. Since pores have lower gray values than grains, the upper threshold for pores corresponds to actually the lower threshold of the grains. Here, we immediately see the main problem. The surrounding air has the same gray value as the pores. If we apply thresholding like this, the software selects everything, including the air outside the sample. To fix this, under Editable Area, I change the option from Everywhere to Inside Bulk Volume Segment. This ensures that only pores inside the sample are selected. Another very important setting is Modify Other Segments. I change this from Override All to Allow Overlap. This allows voxels to belong to more than one segment. Otherwise, the pore voxels would be removed from the bulk volume, which we don't want to. Now I click Apply. It may take a couple of seconds, and perfect. The surrounding air is no longer selected. If I turn off the bulk volume using this visibility icon, I can clearly see only the pores, and very nicely in 3D. Now that we have both the bulk volume and the pores, we can calculate their volumes. We have to make sure both segments are visible, then go to the module finder and select Segment Statistics. In the Segment Statistics module, I make sure the correct segmentation is selected. I choose Table as the output and click Apply. A table appears showing the calculated volume for each segment. We now have the bulk volume and the pore volume. Porosity is simply calculated as pore volume divided by bulk volume, and if we want it as percentage, multiplied by 100. Using the values from the table, the porosity comes out to approximately 22.5%, which is a very typical value for this type of sandstone sample. And that's it. I hope you liked the video, and if you have any questions, feel free to ask.